Tonight, we're going to talk about the fact that in the entire history of our species, the only place any human being has ever been is the Moon. Not Mars, not an asteroid, not anywhere else. 28 people have left the region immediately around the Earth, and every single one of them went to the same destination. The furthest any human has ever traveled from this planet is about 253,000 miles. That record was set 4 months ago, in April of 2026, and it broke a record that had stood since 1970. You probably assume you know why. Most people do, and the answer most people give is money. That answer is right, and it only covers half of it. Money explains the 54-year gap between the last Apollo crew leaving the Moon and the next crew arriving. It explains why the program stopped. It is a story about budgets and politics and a race that ended, and there is nothing frightening in it. It does not explain why, with a working program and renewed funding, the destination is still the Moon. There is a second answer underneath the first, and it is the one this video is named after. It is about what happens to a human body outside the protection of this planet over time, and it is a problem that money does not straightforwardly solve. By the end of tonight, you will know exactly how far anybody has actually gone, and how small that distance is against anything else. You will know the names and dates of everyone who left. You will know what stopped it, honestly, without the version where physics gets blamed for a political decision. And you will know the 4 separate things that make going anywhere further genuinely hard, 3 of which have measured numbers attached, and 1 of which has never been solved. 10 sections. Each one stands on its own. If you drift off during Section 5, you will not have missed anything you need for Section 6. Everything measured will be called a measurement. Everything estimated will be called an estimate. And where the honest answer is that nobody knows, you will get that instead of a guess. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the number, because everything in tonight's video is a reaction to how small it is. On April 6th of 2026, 4 people passed behind the far side of the Moon and reached a distance of 252,756 miles from the Earth. Their names are Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. The first 3 are NASA astronauts. Hansen is Canadian. The mission was Artemis II. It launched on April 1st and it came down in the Pacific on April 10th, 10 days later. That is the record. It is the greatest distance any human being has ever been from this planet, and it is 4 months old. The record it broke was set on April 15th of 1970 by Jim Lovell, Jack Swigert, and Fred Heise at 248,655 miles. There is a detail in that mission worth knowing now, because it comes back in Section 9, and it is the reason the number is what it is. Apollo 13 was supposed to land. The plan was a landing site in the Fra Mauro Highlands, and the crew were about 200,000 miles out when an oxygen tank in the service module ruptured, roughly 56 hours into the flight. The landing was abandoned immediately. What was left was the problem of getting 3 men home from most of the way to the Moon with a crippled spacecraft. The solution was to stop fighting the trajectory and use it. The crew fired the lunar module's engine to put the spacecraft onto a path that would loop around the Moon and return to Earth without further intervention. That path took them around the far side, further out than the Moon itself, which is why the record is what it is. That was Apollo 13, and the reason they hold the old record is that their mission went wrong. An oxygen tank ruptured on the way out, the landing was abandoned, and they had to loop around the Moon on a wider path than planned in order to get home. The furthest any human had ever been from Earth, for 56 years, was a distance reached by accident during a failure. There is a detail in that record worth pulling out, because you may have noticed something odd about the number. The Moon sits at an average distance of about 238,900 miles. Artemis II reached 252,756. So the crew went about 14,000 miles further from Earth than the Moon usually is. Two things account for that. The first is that the Moon's orbit is not a circle. It is an ellipse, and the distance varies from about 225,600 miles at its closest to about 252,000 at its furthest. Those 2 points have names, perigee and apogee, and the difference between them is roughly 26,000 miles, which is more than 3 Earth diameters. If you have ever heard the phrase supermoon, that is what it refers to. A full moon occurring near perigee looks slightly larger than one apogee, by around 14% in diameter, which is a real difference and a difficult one to notice by eye without a photograph to compare. The second reason is the trajectory. Artemis II did not stop at the Moon. It passed behind the far side and continued outward before the Moon's gravity turned it back, so the crew reached a point beyond the Moon itself. Apollo 13 did the same thing for the same reason, which is why its record was also greater than the Moon's average distance. So when you hear that somebody has gone further than anyone in history, the mechanism is not a more powerful rocket. It is a slightly different loop around the same object, flown when that object happened to be a little further away. Now let me make 253,000 miles mean something, because on its own, it is just a large number, and large numbers stop registering. The International Space Station orbits at about 250 miles up. Read those two figures next to each other, 253,000 and 250. Nearly every human being who has ever gone to space has gone to that second number. More than 700 people have flown above the recognized boundary of space, and the overwhelming majority of them went to somewhere between 100 and 300 miles up and came back. If the distance to the Moon were the length of a football field, the space station would be about an inch off the goal line. That is not a criticism of anybody. Low Earth orbit is where the useful work is, it is where the station is, and getting there is genuinely difficult. But it is worth being clear that when you hear that somebody has gone to space, what has almost always happened is a trip to a height that a commercial airliner would cover horizontally in half an hour. You can go further than that on the ground, and this is the comparison I find most useful. If you have flown from London to Sydney, you covered about 10,500 miles, 24 round trips of that flight, and you have travelled the distance from here to the Moon. Or take the circumference of the Earth, which is about 24,900 miles at the equator. 10 and a bit laps of the entire planet gets you to lunar distance. That is the furthest edge of everywhere any human has ever been. 10 laps of this planet, laid out in a straight line. It is a genuinely small number, and the reason it feels large is that you cannot walk it. Distance in space is not difficult because of how far it is. It is difficult because of what you have to do to cross it, and because of what happens to you while you are crossing. Now push the comparison outward, because this is where it stops being funny. The closest Mars ever gets to Earth is around 34 million miles, and that only happens during a favourable alignment that comes around roughly every 2 years. Most of the time it is considerably further. 34 million against 253,000. Mars, at its very closest, is about 134 times further away than any human has ever been. And that is the nearest planet. Go further out, and the numbers stop being comparable at all. Jupiter at closest approach is around 365 million miles, which is more than 1,000 times the record. Neptune sits at around 2.7 billion. Then there is the number that ends this section. 1 light year, the distance light covers in a year, is about 5.88 trillion miles. Divide that by the human distance record, and you get roughly 23 million. You would have to make the furthest journey any person has ever made, and then make it again, 23 million times over, to cover a single light year, and the nearest star is 4.24 of them. I want to be careful here, because that comparison can be used dishonestly, and I do not want to do that. Nobody has ever claimed we were close to interstellar travel. The point of the number is not that we have failed at something we were attempting. The point is calibration. When you hear about missions to Mars, or about becoming a multi-planet species, or about reaching another star, it is worth having the actual scale in your head. The entire achievement of human spaceflight, 65 years of it, fits inside 250,000 miles. There is a second record worth knowing, because it is about speed rather than distance, and it is even older. The fastest any human being has ever traveled is about 24,791 miles per hour. That was Apollo 10 in May of 1969 on the way back from the moon, and it has stood for 57 years. You are moving at about 1,000 miles per hour right now from the Earth's rotation, if you are somewhere near the middle latitudes. So the human speed record is roughly 25 times faster than the ground under you is already going. It is also, and this is the part that matters for tonight, about 0.0037% of the speed of light. Both records, distance and speed, come from the same period and the same program. The distance record has been broken once, 4 months ago, by about 1.5%. The speed record has not been broken at all. Where should the boundary of space even be, since I have used the phrase several times? The most widely used definition is the Kármán line, at 62 miles up, named after Theodor von Kármán, who calculated the altitude at which an aircraft would need to travel at orbital speed in order to generate enough lift to stay up. Above that height, flying and orbiting stop being different activities. The United States Air Force and NASA have historically used 50 miles instead, which is why a small number of pilots are considered astronauts under one definition and not the other. Either way, the boundary sits at a height you could drive in an hour if the road went straight up. That is where space starts, and 253,000 miles is where we have got to. One more figure, and then the section closes. The Voyager 1 spacecraft, launched in 1977, is currently around 15 billion miles away. It is the most distant object humans have ever built, 15 billion, against a human record of 253,000. Our machines have gone about 60,000 times further than our bodies. That gap is the subject of the rest of this video. If you take one thing from this section, make it the ratio between those last two figures. Our machines are 60,000 times further out than our bodies have ever been, and the machines have been going since the 1970s, while the human record moved by 1.5% in 56 years. That is the first section. The furthest anybody has ever been is 252,756 miles, set in April of this year by 4 people on Artemis II. Breaking a record set by accident during a failed mission in 1970. The space station sits at 250 miles. Mars at its closest is 134 times the record. A light year is 23 million times it. You could fit everyone who has ever left Earth orbit into a single bus. 28 people. That is the complete list for the whole of human history. And this section goes through it because the names matter and because the shape of the list tells you something. Start with the boundary, since it needs defining. Low Earth orbit is the region where the space station sits, a few hundred miles up. It is inside the Earth's magnetic field, which matters enormously and is the subject of Section 4. Everybody who has ever flown a space shuttle mission, everybody who has served on the station, every cosmonaut on Mir, every private passenger on a recent commercial flight has stayed inside it. Leaving it means going far enough out that the Earth's magnetic protection is behind you rather than around you. Only Apollo did that, and now Artemis. If you have ever wondered why the number of people who have been to space sounds large, While the number who have left Earth orbit sounds tiny, that boundary is the reason. They are two different achievements, and the same word is used for both. More than 700 people have been to space by the usual definition. 28 have left the neighborhood. You can hold the second number in your head. That is the point of it. Here is the list. Apollo 8, December of 1968. Frank Borman, Jim Lovell and Bill Anders, the first humans to leave Earth orbit and the first to see the far side of the moon with their own eyes. They did not land. They went into lunar orbit, went around 10 times and came home. Anders took the photograph of the Earth rising over the lunar horizon that became one of the most reproduced images of the century. Apollo 10, May of 1969. Thomas Stafford, John Young and Gene Cernan. A full dress rehearsal that went everywhere except the surface. Stafford and Cernan took the lunar module down to about 9 miles above the ground and then came back up without landing, which is one of the more remarkable exercises in institutional discipline in the history of exploration. Michael Collins, Ken Mattingly, Ronald Evans and the others traveled 250,000 miles, went around the moon alone, and came home without ever setting foot on it. The 12 who walked are worth naming individually, because you can hold 12 names, and because after this section the video is about why the list stopped growing. Neil Armstrong and Buzz Aldrin on Apollo 11. Pete Conrad and Alan Bean on 12. Alan Shepard and Edgar Mitchell on 14. David Scott and James Irwin on 15. John Young and Charles Duke on 16. Gene Cernan and Harrison Schmitt on 17. 12 people, across 3.5 years, between July of 1969 and December of 1972. The great majority of them have since died. This was a list of men in their late 30s and early 40s in 1970, which makes the survivors well into their 90s now, and the number who are still alive is very small and shrinking. That is worth stating plainly rather than sentimentally. There will come a point, and it is not far away, at which nobody alive has stood on another world. There is a companion fact that gets left out of almost every telling, and it is about the other 12. For each landing, one crew member stayed in orbit. Michael Collins on 11, Dick Gordon on 12, Stuart Rooser on 14, Alfred Worden on 15, Ken Mattingly on 16, Ronald Evans on 17, plus the crews of 8, 10 and 13, none of whom landed at all. Those men travelled 250,000 miles and came home without touching the surface. Worden, on Apollo 15, spent 3 days alone in lunar orbit. When his spacecraft passed behind the moon, radio contact with Earth was cut entirely, and for about 48 minutes on each orbit he was the most isolated human being who had ever existed, with the entire moon between him and every other person alive. He was asked about it repeatedly afterward, and consistently said he enjoyed it. Ken Mattingly's story is the one most people half know. He was originally assigned to Apollo 13, and was removed days before launch because he had been exposed to German measles and had no immunity. Jack Swigert replaced him. Mattingly never developed the illness, and he flew to the moon 2 years later on Apollo 16 instead. Then it stopped. Cernan and Schmitt lifted off from the lunar surface on December 14th of 1972. Cernan was last up the ladder, which makes him the last person to have stood on another world. And then, for 53 years and 4 months, nobody left Earth orbit at all. Not one person, not one mission. The space shuttle flew 135 times and never went above about 400 miles. The station has been continuously occupied since 2000 at 250 miles. Every space station, every satellite servicing mission, every record for time in orbit, all of it happened inside that thin shell. The nearest anybody came to breaking out was in September of 2024, when a private mission called Polaris Dawn raised its orbit to around 870 miles, the highest any crew had flown since Apollo. That is higher than anything in 50 years, and it is still not 1% of the way to the moon. Then, in April of 2026, Artemis II, Wiseman, Glover, Koch and Hansen. 10 days, a loop around the far side, and home. Christina Koch became the first woman ever to leave Earth orbit, 57 years after the first man did. Jeremy Hansen became the first person from any country other than the United States to do it. That brings the total to 28. The mission itself is worth a little more detail, because the shape of it explains what a modern lunar flight actually involves. The first day was spent in Earth orbit, deliberately, running checks on the spacecraft before committing to the departure burn. That is a discipline Apollo also used, and the logic is straightforward. Once the burn happens, you are going, and the checks are much easier to act on while you are still somewhere you can come down from. The departure burn is called translunar injection, and it raises the spacecraft's speed enough to leave Earth orbit and coast outward. After it, the flight is largely a matter of waiting. The outbound coast took about 4 days. During it, the crew ran systems tests, including a demonstration of flying the spacecraft manually using the discarded upper stage as a target, which is a rehearsal for docking with a lander on a later mission. On the 4th of April, they lost the Earth behind the Moon. That is the part with no equivalent anywhere else. Passing behind the far side, the Moon physically blocks the signal, and communication stops. It is not a fault, and it is not an emergency. It is geometry, and it lasts around half an hour. And during it, the crew are the only humans who cannot be reached by anybody. Then the far side itself, which fewer than 30 people in history have seen directly. It looks nothing like the face you know. There are almost none of the dark planes that make up the pattern people recognize, and the surface is far more heavily cratered. Then the turn, the peak distance, and 4 days back. Splashdown was in the Pacific off San Diego on April 10th. 10 days, most of it coasting, one loop, and a record that had stood for 56 years. There is something about the dates that you may not have registered, and it is the fact I find hardest to hold. The entire history of humans leaving Earth orbit, up until this year, took place in a window of 4 years and 1 month. December of 1968 to December of 1972. Everything, every departure, every landing, every one of the 12 people who walked. 4 years. If you were born after 1972, and most people alive now were, then for your entire life until 4 months ago, no human being had been further than a few hundred miles from the surface of this planet. You have lived through the whole gap. If you are under 53, you have never been alive during a period when anybody was going anywhere. That is not a fact about spaceflight. It is a fact about you, and it is worth noticing because it shapes what you assume is normal. A person born in 1960 grew up watching people leave. A person born in 1980 grew up with the shuttle going in circles. Now, the thing about that list which is worth noticing, and which I did not expect when I first laid it out, every single one of those people went to the same place. Not one human being in history has traveled to any destination other than the Moon. Every crewed mission that has ever left the Earth's immediate neighborhood has gone to one object, the closest one, and come back. There is no second destination. There is no partial attempt at one. In 65 years of human spaceflight, the itinerary has exactly one entry on it. That is a strange fact, and it does not get said plainly very often, because the coverage of spaceflight tends to be about individual missions rather than the pattern across all of them. It is worth being precise about what happened in that 53-year window, because a lot of extraordinary spaceflight took place inside it, and none of it went anywhere. Skylab, the first American space station, flew from 1973 using leftover Apollo hardware. 3 crews lived aboard it, the longest for 84 days. The Apollo-Soyuz mission of 1975 docked an American and a Soviet spacecraft together in orbit, which was politically remarkable and physically about 140 miles up. Then the United States flew nobody at all for almost 6 years, between 1975 and the first shuttle flight in 1981. The shuttle flew 135 missions over 30 years. It deployed and repaired the Hubble Space Telescope, built most of the space station, and lost 2 crews. Its highest flights, on Hubble servicing missions, reached around 380 miles. Mir was occupied almost continuously from 1986 to 1999. The International Space Station has been permanently inhabited since November of 2000, which means that at the time of this recording there has been at least one human being off this planet, continuously, for over 25 years. Every single one of those flights stayed inside the shell. So the gap is not a story about spaceflight stopping. Spaceflight expanded enormously. It is a story about spaceflight becoming an activity conducted entirely at one altitude. One more observation before this section closes, and it is about time rather than distance. The longest any human being has ever been away from the Earth's immediate vicinity is about 12.5 days. That was Apollo 17. Compare that to the duration record set in low Earth orbit. Valery Polyakov spent 437 continuous days on Mir. Frank Rubio spent 371 days on the station in a single stint, which was not planned and happened because his return vehicle developed a leak. So we have kept people in space for well over a year. We have kept people beyond Earth orbit for under a fortnight. Those are different problems, and section 9 is about why. One more comparison before this section closes, and it is the one that makes the list feel its actual size. More people have climbed Mount Everest in a single busy season than have left Earth orbit in the whole of history. Several thousand people have summited Everest since 1953. 28 have gone beyond the Earth's immediate neighborhood since 1968. Those 2 activities started within 15 years of each other. One became something a well-prepared and well-funded person can arrange. The other has happened 28 times, entirely at the direction of governments, and cannot be arranged at any price. That is not going to change soon, and the rest of this video is about why. That is the second section. 28 people have left Earth orbit across 10 missions spanning 1968 to 2026 with a 53-year gap in the middle. 12 of them walked on the moon. Every one of them went to the moon and nowhere else. And no crew has ever spent more than about 12 days outside the protection of this planet. Here is the part where I have to be honest with you, and it is not the answer the title of this video sets you up for. Nobody stopped going to the moon because it was too dangerous. Nobody stopped because of radiation, or because a barrier was discovered, or because the physics turned out to be worse than expected. We stopped because the money stopped, and the money stopped because the reason for spending it had gone away. That is the whole of it for the period between 1972 and now, and if I dressed it up as something more dramatic, I would be lying to you. The frightening part of tonight's video is real, and it is coming, but it is not this. This part is a story about budgets. Start with the size of the spending, because it is difficult to believe if you have only seen modern figures. At its peak in 1966, NASA received about 4.4% of the entire United States federal budget. Take a moment with that. Not 4.4% of the science budget or the research budget, of the whole thing, everything the federal government spent that year. And roughly $1 in every 23 went to the space program. For comparison, NASA's share today runs at around 0.4%, which is roughly a tenth of what it was. Apollo employed about 400,000 people across NASA and its contractors at its height. Not 400,000 over the life of the program, 400,000 at once. The total cost of Apollo was around $25 billion in the money of the time. Adjusted forward, estimates put it somewhere in the region of $250 billion in today's terms, and some methods put it higher. That was not a science budget, it was a national mobilization, and it was funded because of what it was for. You can check that budget figure against something in your own life, which makes it land differently. If $1 in 23 of all federal spending went to the space program, and you think about what fraction of your own income you would have to spend to match that proportion, you get a number most people would notice. And it was sustained for years, not for one budget cycle. There is nothing comparable in peacetime spending on anything that was not a war or a welfare program. That is the scale that put 12 people on the moon, and it is worth having in mind whenever somebody says we could go back if we wanted to. We could. That is what wanting to costs. Now the reason, which is the part that gets sanded down in retellings. Apollo was not primarily an exploration program. It was an instrument of the Cold War. The Soviet Union had put the first satellite in orbit in 1957, the first animal shortly after, the first man in April of 1961, and the first woman in 1963. The United States was losing a public competition in a highly visible arena, and that competition was understood by both sides as a demonstration of technological and industrial capability with military implications. John Kennedy's speech to Congress committing to the moon came in May of 1961, 6 weeks after Yuri Gagarin flew. There is a recording of a conversation between Kennedy and the NASA administrator James Webb from November of 1962, in which Kennedy says plainly that he is not that interested in space, that the program is enormously expensive, and that the reason for doing it is that it has become a matter of national prestige against the Soviet Union. That is not a hostile characterization. It is the President of the United States describing his own reasoning to the man running the agency. Once the goal was met, the reasoning stopped applying. If that sounds cynical, notice what it predicts. It predicts that public attention would collapse the moment the race was over, and that is exactly what the record shows. Armstrong and Aldrin landed in July of 1969. Public interest fell away almost immediately afterward. By Apollo 13, the television networks were not carrying the broadcasts live, which is part of why the accident came as such a shock to the public. There is a specific moment that captures it better than any statistic. Apollo 17 launched at night in December of 1972, and it was the only night launch of the program. A Saturn V lifting off in darkness was visible for hundreds of miles, and it remains one of the most photographed events in spaceflight. It was also the last one, and everybody involved knew it at the time. The vehicles for the next 3 missions had been cancelled 2 years earlier, so the most spectacular launch of the entire program was a closing ceremony, and the people watching it understood that. The cancellations came fast. Apollo 18, 19 and 20 were all planned, hardware was partly built, and all 3 were cut. The final cancellations were announced in 1970, before Apollo 14 had even flown. So the last 3 missions to the moon were cancelled while the program was still going, and the equipment already paid for was left over. One of the unused Saturn V rockets is lying on its side at the Kennedy Space Center as an exhibit. There are 2 others. There are complete flight-ready rockets, built to go to the moon, that were turned into museum pieces because the money to fly them was withdrawn. There is a detail about the ending that is worse than the cancellations, and it is the one that made the decision permanent rather than reversible. The production line was shut down, and the tooling was disposed of. A Saturn V was not a design sitting in a filing cabinet. It was a manufacturing capability, specific jigs, specific fixtures, specific machines, and several thousand people who knew how to operate them. When the orders stopped, the contractors moved those people onto other work, and the hardware was scrapped or repurposed. There is a persistent story that the blueprints were lost. That is not accurate. The documentation exists in enormous quantity. What was lost is harder to replace than drawings. It is the accumulated practical knowledge of how to actually build the thing, which lives in the hands of people who have done it and in the tooling they used, and none of that survives a decade of not doing it. So when the question of returning to the moon came up in the 1980s and again in the 2000s, the answer was never simply to build more Saturn Vs. Everything had to be started again. That is why the Space Launch System took as long as it did, and it is why parts of it are descended from Space Shuttle hardware rather than Apollo hardware. Shuttle was the capability that still existed. If you want one lesson from that, it is that a capability is not a document. It is people and tools, and both decay on a timescale of years. What replaced Apollo tells you what the priorities became. The Space Shuttle was designed to be a reusable vehicle for operating in low Earth orbit, and it was justified largely on cost and on serving satellites and a station. It was never intended to go anywhere else. The decision to build it was, in effect, a decision that human spaceflight would be an activity conducted a few hundred miles up. That decision held for 40 years. There is one more thing about the money that puts the modern situation in perspective, and it cuts in the opposite direction to everything above. NASA's budget today, at around 0.4% of federal spending, is smaller as a share than it was. In absolute terms, adjusted for inflation, it is not as far below the Apollo peak as the percentage suggests, because the federal budget as a whole has grown enormously. The agency currently receives roughly $25 billion a year. That is a large amount of money by any ordinary standard. It is not a starved organization. What changed is not only the size of the budget but what it is spread across. Apollo was one program with one goal and near total priority. The modern agency runs planetary science, Earth observation, astrophysics, aeronautics, the space station, and a crewed exploration program simultaneously, and each of those has a constituency. So the honest framing is not that we cannot afford to go. It is that going has to compete with everything else the agency does, and it has not consistently won that competition. Now, the honest complication, because there is one, and it cuts against the simple story. It is not the case that nobody tried in between. Several programs were begun and cancelled. The Space Exploration Initiative was announced in 1989, proposing a return to the Moon and then Mars. Cost estimates came back at several $100 billion, and it never received meaningful funding. The Constellation program began in 2004 with the same broad aim, ran for about 6 years, consumed roughly $9 billion, and was cancelled in 2010 after a review found it was behind schedule and underfunded. Artemis, which finally worked, was formally named in 2019 and had roots going back further. Artemis I flew uncrewed in November of 2022. Artemis II flew with a crew in April of 2026. So the gap was not one decision, it was a repeating pattern. A program is announced, it is funded at a level well below what it requires, it slips, and a subsequent administration cancels it. The recurring problem is that a Moon or Mars program takes longer than a political term. Something requiring 15 years of sustained funding has to survive several changes of government, and until Artemis, none of them did. That is the real answer for the gap, and I want it stated clearly before the rest of the video, because a great deal of coverage implies we were held back by physics when we were held back by appropriations. But here is the turn, and it is the reason this video is not over at section 3. Artemis exists now. It is funded, it has flown a crew, and there are dates on the calendar for a landing, and the destination is still the Moon. The program that finally broke the 53-year gap did not aim past it. Artemis IV is targeting the lunar South Pole in 2028. There is no crewed mission to anywhere else on any agency's schedule with a real date attached. So the money problem, which explains everything up to now, does not explain what happens next. There is money, there is political will, there is working hardware, and the itinerary still has one entry on it. The reason for that is physical, and it starts in the next section. There is one further consequence of the political explanation that is worth drawing out, because it changes what you should expect from here. If the constraint is political rather than physical, then it is not permanent, and it does not improve on its own either. It improves when the reasons change. Apollo happened because two governments were competing in public. Artemis is happening now for a mixture of reasons that include international competition again, alongside science and industrial policy. That is not a criticism. It is an observation that the thing which reliably produces sustained funding for human spaceflight is a rivalry, and that when the rivalry fades, so does the money. If you want a prediction that follows from this video, rather than from optimism, it is that the pace of the next 15 years will track the intensity of competition far more closely than it tracks any technical development. That is the third section, and it is the honest half of the answer. We stopped going to the moon because Apollo was a Cold War program that ended when it was won, not because anything out there stopped us. 4.4% of the federal budget became 0.4%. 3 built rockets became museum exhibits, and every attempt to restart it for the next 40 years died in the gap between how long the engineering takes and how long the government lasts. There is something around this planet that you cannot see, that was not known about until 1958, and that every human being who has ever left Earth orbit has had to pass through. It is the reason low Earth orbit is a fundamentally different place to be than anywhere beyond it, and it is where the physical half of tonight's answer starts. Start with the discovery, because it happened on the first thing the United States ever put in orbit, and it happened by accident. Explorer 1 launched on January 31st of 1958. It was small, about 30 pounds, and it carried an instrument built by a physicist named James Van Allen at the University of Iowa. The instrument was a Geiger counter designed to measure cosmic rays. It is worth remembering what the context was. Sputnik had gone up 4 months earlier, and the United States had failed a launch attempt on live television in December. Explorer 1 was the recovery, and it was assembled and flown in under 3 months. The readings that came back were strange. At low altitudes, the counter reported what was expected. At higher altitudes, it reported 0. 0 is not a plausible reading for cosmic rays. Space is not empty of radiation. One of Van Allen's graduate students, Carl McIlwain, worked out what had happened. The counter was not detecting nothing. It was being saturated. The radiation was so intense that the instrument was overwhelmed and had stopped registering counts at all. The Earth was surrounded by regions of trapped, high-energy charged particles, far more intense than anybody had predicted. They are called the Van Allen belts, and they are one of the few things in space named after a living person at the time of discovery. You are sitting underneath all of this right now, and it is worth being specific about how much protection you personally have. 2 layers. The first is the magnetic field, which starts deflecting charged particles tens of thousands of miles above you. The second is the atmosphere, which is the larger contributor at ground level. The column of air above your head is equivalent, in shielding terms, to something like 30 feet of concrete. Between them, the dose you receive from space is a small fraction of your annual radiation exposure, most of which comes from radon in the ground and from medical imaging rather than from anything overhead. If you live at high altitude, the space contribution goes up because there is less air above you. If you fly regularly, it goes up further. And aircrew are among the most exposed occupational groups on the planet for exactly that reason. Everything in the rest of this video is about what happens when you take both layers away. Here is what they are. The Earth has a magnetic field, generated by molten iron circulating in its outer core. That field extends far out into space. Charged particles, arriving from the Sun and from beyond the solar system, cannot cross magnetic field lines freely. They get caught. Once caught, they spiral back and forth along the field lines, bouncing between the north and south polar regions, and they can stay trapped for a very long time. The result is two donut-shaped regions of concentrated radiation around the planet. The inner belt sits from roughly 400 miles out to around 6,000 miles, and it is dominated by electrons. The boundaries move, they swell during solar storms and contract when the sun is quiet, and a third temporary belt has been observed forming and then dissipating. There is an episode from 4 years after the discovery that tells you how seriously the belts were taken and how badly the consequences were understood. On July 9th of 1962, the United States detonated a nuclear device about 250 miles above the Pacific Ocean. The test was called Starfish Prime, and the yield was 1.4 megatons. The visible effects were dramatic. The sky over Hawaii, nearly 900 miles away, lit up, and streetlights failed in Honolulu. The effect that mattered lasted far longer. The explosion injected an enormous quantity of high-energy electrons into the Earth's magnetic field, and those electrons were trapped exactly the way natural particles are trapped. An artificial radiation belt formed around the planet. It damaged or destroyed a third of the satellites in low Earth orbit at the time, some immediately and some over the following months, including Telstar 1, the first commercial communications satellite, which had launched the day after the test. Parts of that artificial belt persisted for years, so within 4 years of learning that the Earth had radiation belts, we accidentally made another one and disabled a significant fraction of everything then in orbit. It is one of the clearest demonstrations available that the region around this planet is a system rather than empty space, and that things put into it stay there. Now the two things that follow from this, and they point in opposite directions. The first is that the belts are dangerous. Passing through them without shielding, slowly, would deliver a serious dose. The second, and this is the one that matters more, is that the belts are evidence the shield is working. Those particles are trapped because the Earth's magnetic field caught them. They are not reaching the surface. They are not reaching the space station. Everything inside that field is being protected from the thing the field has captured, which means the space station, at 250 miles, is sitting underneath the whole arrangement. The station is not in deep space. It is in a sheltered pocket inside the field below the inner belt, and that is the single biggest reason a person can live there for a year and come home. Frank Rubio spent 371 days on the station. That is possible because of where the station is, not because we have solved the problem of keeping humans alive in space. Now, how Apollo dealt with the belts, because there is a persistent claim online that crossing them should have been fatal, and it is worth addressing directly with the actual numbers. The trajectories were designed to minimize exposure. The flight paths crossed the belts at an angle that avoided the densest regions and passed through the thinner edges, and the crossing was fast. The spacecraft was moving at around 25,000 miles per hour after the burn that sent it toward the moon. So the transit through the belt region took a matter of tens of minutes rather than hours. The doses were measured. Every Apollo crew wore dosimeters, and the results were published. The average total dose across an entire Apollo mission was on the order of a fraction of a rem, or a few millisieverts. Apollo 14 recorded the highest of the landing missions at around 1.14 rem, roughly 11 millisieverts. To put that against something familiar, a single computed tomography scan of the abdomen delivers something in the range of 10 millisieverts. Natural background radiation on Earth gives most people somewhere around 3 millisieverts a year. So an Apollo crew, for a mission of up to 12 days, including the belt crossings and the time on the surface, received something comparable to a medical scan. That is a genuinely reassuring number, and it is why the belts are not, on their own, the answer to tonight's question. There is a piece of context that makes those Apollo numbers more meaningful, and it is about where the field comes from. The Earth's magnetic field is generated in the outer core, where molten iron is circulating. That circulation is driven by heat leaving the core and by the planet's rotation, and the process is called a dynamo. It is not a permanent feature. The field reverses polarity at irregular intervals, averaging a few 100,000 years, and during a reversal it weakens substantially for a period before rebuilding in the opposite orientation. The last full reversal was around 780,000 years ago. The field also is not uniform. It is currently weakening in some regions, which is why the South Atlantic anomaly is growing and being monitored. The reason to know that is not alarm. Life on Earth has survived every reversal in the record with no evidence of associated extinction, largely because the atmosphere does most of the shielding work at the surface. The reason to know it is that the protection this planet provides is an active process, produced by circulating metal 1,800 miles beneath you. And it is the single feature that separates the space station from everywhere else humans might go. Mars lost its equivalent about 4 billion years ago and has never got it back. I want to be very clear about what that does and does not show, because this is the point where the reassuring number gets misused in both directions. It shows that a short trip through the belts on a fast trajectory is survivable and was survived 24 times. It does not show that radiation beyond Earth orbit is a solved problem, because the belts are not the main hazard. They are the hazard people have heard of. The dangerous thing is not what the Earth's magnetic field has caught. It is what nothing catches. Beyond the belts, beyond the reach of the field entirely, there is a form of radiation that does not get trapped, cannot be shielded against in any straightforward way, and never stops arriving. Apollo crews were exposed to it for days. A crew going to Mars would be exposed to it for months. That is section 5. One more thing about the belts before this one closes, because it explains something about how spacecraft are routed even now. There is a region over the South Atlantic where the inner belt dips much closer to the Earth than elsewhere, down to a few hundred miles. It is called the South Atlantic anomaly, and it exists because the Earth's magnetic field is not perfectly centered or perfectly symmetrical. The space station passes through it several times a day. Instruments are routinely switched off during those passes, because the elevated particle flux causes errors in electronics. Astronauts have reported seeing flashes of light during transits. The anomaly is being watched closely for a reason beyond satellite operations. It has been growing over recent decades, and in the last several years observations have indicated it may be splitting into 2 lobes. What that means for the field as a whole is argued about. One reading is that it is an ordinary fluctuation of a system that has always fluctuated. Another is that it is an early indication of a larger change in the field structure. Nobody currently claims it predicts a reversal, and I would treat any coverage that says so as ahead of the evidence. So even at 250 miles, inside the shelter, there is one place where the roof dips low enough to matter. It is a useful reminder that the protection is a shape rather than a wall, and that the shape has a flaw in it. Before this section closes, there is a claim you will meet online that is worth handling directly, because it comes up constantly and the honest answer is more interesting than the argument. The claim is that the Van Allen belts prove the moon landings did not happen, on the grounds that no crew could have survived crossing them. The reason that fails is contained in this section. The belts are dangerous over long exposure, and Apollo crossed them in tens of minutes on a path chosen to avoid the worst regions. The doses were measured with dosimeters worn by the crews and published, and they came out comparable to a medical scan. What I find more interesting than the rebuttal is that the objection is pointing at the right hazard for the wrong mission. Radiation genuinely is the obstacle. It is simply not the belts, and it is not a 12-day trip. It is the constant background beyond them, over months, which is sections 5 and 7. So the instinct that something out there makes long human spaceflight hard is correct. It just does not apply to the one journey we have actually made. That is the 4th section. The Earth is wrapped in 2 belts of trapped radiation, found by accident on the first American satellite in 1958, when the instrument reported 0 because it had been overwhelmed. They are dangerous. Apollo crossed them quickly and at an angle, and the measured doses came out comparable to a medical scan, and their existence is proof of the thing that actually matters. The space station sits inside a shelter, and everything past the belts does not. Every Apollo astronaut saw flashes of light with their eyes closed. Not occasionally. Roughly once a minute, in a darkened cabin, with their eyelids shut, they saw streaks and points and bursts of light that were not there. They reported it, it was investigated, and the explanation is the subject of this section. It is the thing that actually stands between us and anywhere else, and unlike the belts in section 4, it has no solution. The flashes are galactic cosmic rays passing through their heads. You have some of them passing through you right now, and that is not a dramatic flourish. It is a rate you can put a number on. At sea level, secondary particles produced by cosmic rays hitting the upper atmosphere are passing through your body at a rate of roughly 100 per second. Muons, mostly, which are produced high up when a primary cosmic ray strikes an air molecule. They are harmless at that rate, and they have been passing through every living thing on this planet for the whole of evolutionary history. The difference in space is not that the particles are new to you, it is that the primaries arrive instead of the secondaries, and the primaries are a completely different proposition. Here is what those are. A galactic cosmic ray is not a ray. It is a single atomic nucleus, stripped of its electrons, moving at a substantial fraction of the speed of light. Most are hydrogen nuclei, which is to say, single protons. About a tenth are helium, and a small fraction, around 1%, are the nuclei of heavier elements, carbon, oxygen, silicon, iron. They come from outside the solar system. The leading explanation is that they are accelerated by the shock waves of supernova explosions over thousands of years until they are moving fast enough to cross the galaxy. They arrive from every direction, all the time, at a rate that does not vary much. Now the two properties that make them different from every other radiation problem. The first is energy. A cosmic ray iron nucleus carries an enormous amount of energy for a single particle. When it passes through matter, it does not deposit that energy gently. It leaves a track of destruction along its path, ionizing everything it touches for a considerable distance. The flashes the astronauts saw were particles passing through the retina, or in some cases through the optic nerve or the visual cortex directly, and triggering a signal that the brain interpreted as light. There was no light. The particle was the signal. That effect was studied deliberately. On Apollo 16 and 17, the crews wore a device to record the timing of the flashes against detected particles, and the correlation held up. You can put a scale on that energy. A single cosmic ray iron nucleus can carry more kinetic energy than a fast-moving grain of sand, concentrated into one atomic nucleus. The most energetic cosmic ray ever detected, recorded in Utah in 1991, and nicknamed the Oh My God particle, carried roughly the energy of a baseball thrown at around 60 miles per hour in a single subatomic particle. Nothing that extreme is relevant to a spacecraft, because particles at that energy are vanishingly rare. The point of the comparison is what a single nucleus is capable of carrying, and why the ordinary ones cannot be treated like the radiation anybody is used to. The second property is the one that makes this a hard problem rather than an engineering problem. You cannot easily shield against them, and the obvious approach makes things worse. Here is why. When a high-energy nucleus strikes a solid material, it does not simply stop. It shatters the nuclei it hits, and those fragments continue onward, and they in turn hit more nuclei. One incoming particle becomes a shower of many secondary particles. That process is called spallation, and the practical consequence is that a thin or moderate layer of shielding can deliver a higher dose to whatever is behind it than no shielding at all, because a single hard-to-stop particle has been converted into a spray of easier-to-absorb ones, all of which now deposit their energy in the crew. To actually reduce the dose, you need enough mass to absorb the entire shower. Estimates for that run into the range of several feet of water, or the equivalent, wrapped around the habitable volume. Water weighs about 62 pounds per cubic foot. Surrounding a crew compartment with several feet of it produces a mass that is not currently launchable in any realistic architecture. It is worth being concrete about how much mass that is, because the numbers decide the argument. A crew compartment for 4 people on a long mission needs an internal volume in the region of a few thousand cubic feet if the crew are not going to be in a state of permanent misery. Surround something that size with 3 feet of water and you are adding several hundred tons. For comparison, the entire International Space Station, assembled over more than a decade across dozens of launches, has a mass of around 450 tons. So full shielding for one Mars vehicle is comparable to launching another space station, and it has to leave Earth orbit rather than stay in it, which costs far more again. That is the arithmetic, and it is why nobody proposes doing it. The proposals are all about arranging the mass you are bringing anyway. Materials rich in hydrogen do better per unit mass, because hydrogen has a single proton and produces fewer damaging secondaries. Water and polyethylene are the usual candidates, and they help. They do not solve it. So the situation is a constant flux of particles arriving from every direction. That thin shielding worsens and thick shielding cannot be launched. The light flash investigation is worth telling properly, because it is a good example of astronauts reporting something strange and the system taking it seriously rather than dismissing it. Buzz Aldrin mentioned it first, after Apollo 11. He described seeing flashes with his eyes closed during the coast to the moon. Other crews reported the same thing once they were asked. The initial reaction included the possibility that it was a psychological effect of a dark cabin, which is a reasonable first guess, and which turned out to be wrong. For Apollo 16 and 17, NASA flew a device called ALF-MED, which is an acronym for Apollo Light Flash Moving Emulsion Detector. It was a helmet the astronaut wore, containing sheets of emulsion that recorded the tracks of particles passing through. The crew member wore it in darkness and pressed a button each time he saw a flash. Afterward, the emulsion was developed and the recorded particle tracks were compared against the timing of the button presses. The correlation held. The flashes were particles. The rate was roughly 1 every 1 to 3 minutes, which over a 12-day mission comes to several thousand individual heavy particles passing through a person's head, each one leaving a track of ionization behind it. Every crew that went to the moon experienced that. It is one of the most direct pieces of evidence available that the environment out there is doing something to a body continuously, and it was discovered because somebody said what he saw, and somebody else built an instrument to check. Now what it does to a body, and here I have to be careful because this is where the evidence gets thin and the confident claims start. The measured part is the dose, which is section 7. The uncertain part is the biology, and the reason it is uncertain is that nothing on Earth reproduces this kind of exposure. Radiation medicine is built on decades of data from bomb survivors, medical treatment, and industrial accidents, and all of that involves gamma rays and X-rays. Those are photons. A cosmic ray ion nucleus is a completely different kind of insult to a cell, delivered along a track rather than diffusely. There is animal work, rodents exposed to particle beams at accelerator facilities, standing in for cosmic rays, have shown effects on the central nervous system, on cardiovascular tissue, and on cognition in some studies. I would treat that literature with care. The doses are usually delivered in minutes rather than over months. The species is not human, and results have not always replicated. Researchers in the field say so themselves. What is agreed is the direction of the concern rather than its size. Increased lifetime cancer risk is the primary one, and it is quantifiable in a rough way. Beyond that, there are open questions about the central nervous system, about the cardiovascular system, and about degenerative disease, and the honest summary is that nobody can currently give you a number they are confident in. That uncertainty is itself the obstacle. You cannot certify a mission against a risk you cannot quantify. Now the comparison that makes the Apollo numbers make sense. Section 4 said, Apollo crews received doses comparable to a medical scan. That is true, and it is because of one variable, time. The cosmic ray flux is roughly constant. The dose you receive is therefore roughly proportional to how long you are out there. Apollo is 6 to 12 days. A Mars mission is 6 to 9 months each way, plus time on the surface waiting for the planets to line up again for the return, which pushes a realistic round trip to somewhere between 2 and 3 years. Take the Apollo exposure and multiply the duration by a factor of around 100, and the reassuring number stops being reassuring. That is the whole argument, and it is why the moon remains the only destination. A lunar trip is short enough that the cosmic ray dose stays inside acceptable limits. Nothing else is. There is a piece of terminology here worth having, because you will meet it in anything you read on this, and it is rarely explained. The heavy nuclei in cosmic rays get called HZE particles. The letters stand for high atomic number and energy, which is a description rather than a name. They make up only about 1% of the flux by number. They contribute a disproportionate share of the biological damage, because damage does not scale simply with how many particles arrive. A single iron nucleus deposits vastly more energy along its path than a proton does, concentrated into a narrow track. That is why the dose from cosmic rays cannot be summarized by a single number the way an X-ray dose can. The same total energy delivered as a spray of protons and as a handful of iron nuclei produces different biological outcomes, and the factor relating them is estimated rather than measured in humans. If you ever see a confident statement about exactly how dangerous a Mars mission is, that factor is where the confidence is coming from, and it is the softest number in the whole calculation. One more detail, and it is a genuinely strange one. Cosmic ray intensity is not constant over the solar cycle, and it varies in the direction you would not guess. When the sun is most active, cosmic ray levels near Earth are lowest. The sun's expanded magnetic field and stronger solar wind push a fraction of the incoming galactic particles back out of the solar system. So the safest time to travel, as far as galactic cosmic rays are concerned, is during solar maximum, which is also when the sun is most likely to produce the kind of event described in Section 6. That is a genuine trade with no obvious right answer, and it is one of the live arguments in mission planning. There is one honest thing to add before this section closes, because I have spent it describing a hazard and the framing can mislead. Nobody has been harmed by galactic cosmic rays in a way that has been definitively identified. The 24 Apollo astronauts have been followed medically for decades. Studies of their long-term health exist, and they are difficult to interpret because the sample is 24 unusually fit, unusually screened men, which is not a group you can easily compare to anything. Some analyses have suggested elevated rates of cardiovascular disease among those who flew to the moon compared to astronauts who stayed in low Earth orbit. Others have found no significant difference. The sample is far too small to settle it, and it always will be, because there will never be more Apollo astronauts. So the honest position is not that we know this hurts people. It is that we have a mechanism, a measured exposure, and no adequate data on the outcome. And the missions being contemplated involve exposures 100 times larger than anything in the record. That is a different and less dramatic claim than the one usually made, and it is the one the evidence supports. That is the fifth section. Galactic cosmic rays are individual atomic nuclei moving near the speed of light, arriving constantly from outside the solar system, and every Apollo crew watch them pass through their own eyes. Thin shielding makes the problem worse by shattering them into showers. Adequate shielding is too heavy to launch. Apollo survived them because Apollo was 12 days, and Mars is not. In August of 1972, between two Apollo missions, the Sun did something that would have put a crew in serious trouble. Apollo 16 had splashed down in April. Apollo 17 would launch in December. In the gap between them, starting on the 2nd of August, a sunspot region designated MR 11976 produced a sequence of enormous flares over about a week. Nobody was in transit. That is the entire reason this is a piece of history rather than a disaster. This is the 6th section, and it is about the hazard that is different in kind from the one in section 5. Galactic cosmic rays are a constant background. What the Sun does is an event, and events can be survived or they can be fatal depending entirely on when they happen. You have almost certainly seen the harmless version of this, or at least photographs of it. When a large solar event reaches Earth, the particles are funneled by the magnetic field toward the poles and dumped into the upper atmosphere, where they make the air glow. That is the aurora, and when an event is large enough, it is visible much further from the poles than usual. So the thing that would be dangerous to a crew in transit is, down here, a light show. The difference is entirely that you are standing underneath a magnetic field and an atmosphere, and they would not be. Start with what the Sun actually produces, because 3 different things get called solar storms and they behave differently. A solar flare is a sudden release of magnetic energy from the Sun's surface, delivering light across the spectrum, and it arrives at the speed of light with no warning beyond seeing it happen. A solar particle event is the accompanying stream of charged particles, mostly protons, accelerated to high energies and thrown outward. Those take longer to arrive, from tens of minutes to a day or more depending on their energy and the geometry. A coronal mass ejection is a large cloud of solar material thrown outward, arriving over 1 to 3 days. The dangerous one for a crew is the particle event, because the particles are energetic enough to penetrate a spacecraft hull, and there can be very many of them in a short period. Here is why this differs from the cosmic ray problem. Cosmic rays are individually more energetic and essentially impossible to stop. Solar particles are individually less energetic, which means shielding actually works against them, but they arrive in enormous numbers over hours. So the two problems have opposite shapes. Against cosmic rays, shielding barely helps and duration is the enemy. Against solar events, shielding helps a great deal and timing is the enemy. That difference produces the standard proposal for handling solar events, which is a storm shelter. Rather than shielding the whole spacecraft, you shield one small compartment heavily, often by surrounding it with things you are carrying anyway: water tanks, food, waste, equipment. When an event is detected, the crew moves into it and stays until the flux drops. That approach is workable, it has been studied in detail, and versions of it are in the designs of most proposed deep space vehicles. It is a real answer to a real problem. Now the 1972 event and the specific reason it is remembered. The flares of early August produced one of the most intense particle events on record. The particle flux at Earth's distance rose to extraordinary levels. The transit time from the Sun was unusually short, and the event was sustained. Various analyses have been done of what an Apollo crew would have received had they been in transit or on the lunar surface during it. The figures vary depending on assumptions about shielding and about which part of the mission the crew was in, and I want to give you the honest range rather than the dramatic number. Inside the command module, with its shielding, the dose would have been serious but likely survivable, and would have produced acute radiation sickness in most estimates. On the lunar surface in a suit, with essentially no shielding, the dose becomes far worse, and several published assessments put it at or near lethal levels. That second scenario is the one that gets quoted, and it is worth noting that it requires the crew to be outside, on the surface, at the moment of arrival, without the ability to get back to shelter quickly. What is not in dispute is that the event happened, that it was among the largest measured in the space age, and that it fell in a 4-month window between 2 crewed lunar missions. Gene Cernan, who commanded Apollo 17 and flew in December of that year, was asked about it afterward. The program had no capability to protect a surface crew from an event of that size. There was no shelter on the moon. It is worth knowing how that event was measured, since nobody was out there with a dosimeter. Some of it came from satellites, which were in orbit and recording. Some came from ground-based neutron monitors, which detect the secondary particles produced when a solar particle strikes the upper atmosphere. And some of it came, years later, from a completely unexpected direction. Analysis of data from instruments left on the lunar surface by Apollo crews and from spacecraft in transit at the time allowed the event to be reconstructed in more detail than was possible in 1972. So the assessment of what would have happened to an Apollo crew is not a guess made at the time. It is a reconstruction made afterward with better data than the people running the program had while it was happening. Which is worth sitting with for a moment. The decision to fly Apollo 17 in December was made without knowing, in the detail we now know, what had happened in August. Now the part that makes this a live problem rather than a historical curiosity. Solar particle events cannot currently be predicted with useful lead time. We can observe the sun continuously. We can identify active regions that look capable of producing large flares. We can tell you that a region is dangerous. What nobody can do is tell you that a specific flare will occur at a specific time. The warning in practice comes from seeing the flare itself, which gives you the light travel time of about 8 minutes plus however long the particles take to arrive. For a crew near Earth, that is workable, because a storm shelter is a short distance away. For a crew on the lunar surface several miles from their vehicle, it is marginal. For a crew on Mars, it is what they have. And there is a further complication that is easy to miss. The largest events are rare, which sounds reassuring and is not. Rare events over a short mission are unlikely. Over a mission lasting 2 to 3 years, the probability of encountering at least one significant event approaches certainty. Estimates for a Mars round trip generally conclude that a crew should expect multiple events, including possibly a large one. So the mission planning question is not whether a solar event will happen during a Mars mission. It is how many, and how large, and whether the shelter is adequate for the worst one. The storm shelter idea is worth one more paragraph, because the practical version is more mundane and more clever than it sounds. You are already carrying a great deal of mass that has nothing to do with shielding. Water for the crew, food, waste that has not been jettisoned, spare parts, batteries. The insight is that mass is mass. A tank of drinking water absorbs radiation whether or not you intended it to, and water is one of the better materials for the job because of its hydrogen content. So rather than launching shielding, you arrange what you are already launching. Line the walls of one compartment with the water tanks and the food lockers and the waste storage, and you have a shelter that costs you nothing in additional mass. Designs along those lines have been tested on the space station. A configuration using stowage bags and water containers arranged around a crew sleeping area was evaluated as a demonstration of the principle. It works against solar particles. It does very little against the cosmic rays in Section 5, for the reasons that section gave, which means the shelter solves the acute problem and leaves the chronic one untouched, and it is the chronic one that decides where you can go. There is a historical benchmark for how bad it can get, and it is not from the space age. The Carrington event of 1859 is the largest solar storm in the observational record. It is named after Richard Carrington, an English amateur astronomer who happened to be sketching sunspots on the morning of September 1st when he saw 2 patches of brilliant white light appear on the solar surface and fade over about 5 minutes. He had watched a flare happen, in white light, by eye, which is rare enough that only a handful of such observations exist in the whole history of solar astronomy. The particles arrived about 17 hours later, which is unusually fast, and indicates an exceptionally energetic event. It produced aurora visible in Cuba and Hawaii, and induced currents strong enough to shock telegraph operators. There is also evidence in tree rings and ice cores of events considerably larger than Carrington. The best documented is a spike in radiocarbon dated to around the year 774, which appears in tree rings across the world simultaneously, and indicates a particle event perhaps 10 times larger than anything measured directly. Those are called Miyake events, after Fusa Miyake, the Japanese researcher who identified the first one in 2012 by measuring radiocarbon in Japanese cedar trees year by year. That method is worth appreciating. A tree lays down one ring per year and locks in the atmospheric carbon of that year. So a tree that lived through an enormous particle event recorded it, precisely, and kept the record for 12 centuries until somebody thought to look. Several more have since been found, in tree rings and in ice cores at various dates. The one from around the year 774 is the largest identified. Had it happened during the space age, it would have been the defining event of the field. If an event of that magnitude occurred during a crewed deep space mission, no shelter design currently proposed would be sufficient. The probability of that in any given 3-year window is low. It is not zero, and it is not something that can be engineered away. It can only be accepted. There is a modern parallel that makes the warning time problem concrete, and it happened in 2022. A batch of satellites was launched into a very low orbit shortly after a geomagnetic storm. The storm had heated and expanded the upper atmosphere, increasing drag at that altitude beyond what the launch profile assumed. Most of the batch could not raise their orbits in time and re-entered. Nobody was hurt. Hardware was lost. The relevant part is that the storm was known about and the consequence still was not anticipated correctly, in an environment we monitor continuously, a few hundred miles above a planet covered in instruments. That is the state of the art in space weather forecasting. It is far better than it was, it is genuinely useful, and it is not good enough to promise a crew 8 months from home that they will have warning. That is the 6th section. The Sun produces particle events that arrive with essentially no warning, and unlike cosmic rays, they can be shielded against, which is why storm shelters are in every serious deep space vehicle design. In August of 1972, one of the largest events on record occurred 4 months after Apollo 16 came home and 4 months before Apollo 17 went out. A crew on the surface during it would have been in severe trouble, and the program had no way to protect them. Over a mission of 2 to 3 years, encountering at least one such event is not a risk. It is a certainty. Everything in the last 3 sections was mechanism. This section is the measurement, and it exists because somebody had the sense to put a radiation detector inside a spacecraft on its way to Mars and switch it on for the journey. That is the 7th section, and it is the number the whole argument rests on. Here is what happened. The Curiosity rover launched in November of 2011, inside a capsule, on a cruise to Mars that took about 8.5 months. It landed in August of 2012. Bolted inside that capsule was an instrument called the Radiation Assessment Detector, run by a team led from the Southwest Research Institute. The important word in that sentence is inside. The detector was not on the outside of the spacecraft, measuring the raw environment. It was in the position a crew member would occupy, behind the same structure a crew member would be behind, receiving what a person would receive. Nobody had ever done that. Every previous measurement of the deep space radiation environment had been taken by an exposed instrument, which tells you about space but not about what a shielded human would absorb. The result, published in Science in 2013, was a dose rate during the cruise in the range of 1.75 to 3.0 millisieverts per day. Take the middle of that and run it out. Roughly 2 millisieverts a day, for around 250 days of outbound cruise, comes to something on the order of 500 millisieverts, or half a sievert, for the journey out. Double it for the return and you are at about a sievert before any time spent at Mars. Now let me give you the reference points, because a sievert means nothing on its own. Natural background radiation on Earth gives most people around 3 millisieverts a year. So 1 day of the cruise to Mars is roughly comparable to 8 months of ordinary life on the ground. A chest X-ray is around 1/10 of a millisievert. A computed tomography scan of the abdomen is around 10 millisieverts. The occupational limit for a radiation worker on Earth is typically 20 millisieverts per year, averaged over 5 years, with a hard ceiling of 50 in any single year. A career limit for a NASA astronaut has historically been set in the range of a few hundred millisieverts to around 1 sievert, depending on age and sex at the time the limits were written, and has since been revised toward a single standard of about 600 millisieverts for everyone. Put those together and you get the problem stated in one line. The round trip to Mars, with no surface time, delivers something close to or above an entire career limit. That is not a projection or a model. The cruise number is measured by an instrument in the right place, on a real vehicle, on the real trajectory. The career limit is worth explaining properly because it is not a safety threshold in the way the phrase suggests. Radiation exposure limits for astronauts are not set at the level where harm begins. They are set at the level of an agreed increase in lifetime risk of dying from cancer. The standard NASA used for many years was a 3% increase in the probability of fatal cancer over a lifetime, not a 3% chance of cancer. A 3% increase above whatever that individual's baseline risk already was. That translated into different dose limits for different people because the underlying risk varies with age and sex. Younger astronauts and female astronauts had lower limits, which produced the uncomfortable situation of some crew members being eligible for missions that others were not. In 2021, that was revised toward a single limit applying to everybody, set at around 600 millisieverts. So the number is a policy decision resting on a risk model, and the risk model rests on the biology from Section 5, which is the part nobody can pin down. That is worth knowing before anybody tells you a Mars mission is or is not within limits. The limit is a choice about acceptable risk, and the conversion from dose to risk carries uncertainty that is larger than most of the differences being argued about. You have a decision point of your own, buried in those numbers, and it is worth noticing because it changes how the astronaut limits read. Medical imaging is the largest artificial radiation exposure most people receive. A single abdominal scan at around 10 millisieverts is roughly 3 years of natural background delivered in a few minutes, and people accept that routinely because the diagnostic benefit is immediate and concrete. Nobody thinks that is reckless, and it is not. What the astronaut limits reflect is the same kind of judgment applied to a case where the benefit is not medical and the exposure is 100 times larger. That is a harder judgment, and it is made by committees rather than by the person receiving the dose, which is one of the odder features of the whole arrangement. Now the surface, because it is better than the cruise, and that surprises people. The same instrument continued operating after landing, and measured the dose on the Martian surface at around 0.7 millisieverts per day, roughly a third of the cruise rate. Two things account for the improvement. The first is that Mars has an atmosphere. It is thin, about 1% of Earth's pressure, but it still represents a column of material above you, and it absorbs some of the incoming flux. The second is that the planet itself blocks half the sky. Standing on a surface, you are only exposed to radiation from above. Roughly half of what would have hit you is instead hitting the ground on the other side of the planet. That second effect is worth knowing because it points at the main mitigation for a surface mission, which is to put the habitat under something. Regolith piled over a structure, or a lava tube, or a trench, all work by the same principle as the planet itself. So Mars is not the hard part, the transit is. There is something about that instrument worth appreciating, which is how nearly it did not happen. A rover is a mass-constrained object. Every pound of instrument is a pound of something else you cannot carry. And RAD had to justify its place against instruments doing the geology the mission was actually for. It was included because somebody argued that if you are sending a vehicle to Mars anyway, and it has a shielded interior, you should measure what a person inside it would receive, because you will not get another chance for a decade. That argument won. The instrument flew. It was switched on for the cruise, and the result is now the single most cited number in every discussion of human Mars missions. It is a good example of the fact that the most useful measurement is often not the one the mission was built for. Somebody has to notice the opportunity and fight for the mass. Now the honest caveats, and there are several. The measurement was taken during a period of relatively high solar activity, which, as Section 5 explained, means galactic cosmic ray levels were suppressed. During solar minimum, the cruise dose would be higher, perhaps considerably. The capsule Curiosity flew in was not designed as a crew vehicle, and its shielding is not identical to what a crew vehicle would have. Estimates adjusting for a realistic crew module move the number in both directions depending on the design. And the conversion from absorbed dose to biological risk involves a weighting factor for particle type that carries real uncertainty, for exactly the reason Section 5 described. The biology of heavy nuclei is not well characterized in humans. So the honest statement is not that a Mars mission delivers precisely 1 sievert. It is that the cruise dose has been measured directly. It lands in a range that sits at or above career exposure limits for a round trip, and the uncertainty in translating that into a health outcome is itself large. There is a comparison point closer to home that helps calibrate the surface number, and it involves the space station. Crew on the station receive roughly 0.3 to 0.8 millisieverts per day, depending on solar conditions and where in the orbit they are. A 6-month rotation therefore delivers somewhere in the region of 80 to 150 millisieverts. That is a substantial dose by terrestrial standards, several times what a radiation worker on Earth is permitted annually, and it is accepted because the missions are short relative to a career, and the crew are informed volunteers. Notice, though, that the station rate is broadly comparable to the Martian surface rate, and well below the Mars cruise rate. That is the whole geography of the problem in 3 numbers. Inside the magnetic field, moderate. On a planetary surface with some atmosphere and half the sky blocked, moderate. In open space between planets, several times worse, with no way to reduce it and nothing to hide behind. The dangerous part of going to Mars is not Mars. It is the space in between, and there is a lot of it. Now the comparison that closes the argument this video has been building. Apollo 14, the highest dose of the landing missions, recorded around 11 millisieverts across the whole mission. The cruise to Mars delivers that in about 5 days. Not 5 days of a dangerous phase, 5 ordinary days of roughly 250 each way. That is the entire reason the Moon is still the only destination. It is not that Mars is further in a way that costs more fuel, though it does. It is that the trip is long, the exposure accumulates every single day of it, and the total lands somewhere no agency has been willing to sign off on for a crew. A lunar mission is about 12 days. A Mars mission is 2 to 3 years. The hazard is the same hazard. The difference is entirely the clock. There is one more way to hold this number that I find clarifies it better than any of the comparisons above. The dose is a rent you pay per day, and it does not depend on where you are going. A trip to Mars and a trip to nowhere in particular, lasting the same time in the same environment, cost the same. The destination is irrelevant. What you are buying with the dose is time outside the shelter. Which means the question for any deep space mission is not how far, it is how long. That reframing is why the Moon works and nothing else does. The Moon is not close in a way that reduces the hazard per day. It is close in a way that reduces the number of days, and the number of days is the entire bill. 3 days out, 3 days back, a few on the surface, That is the only itinerary anybody has found that keeps the total small enough. That is the 7th section. In 2011, an instrument was flown to Mars in the position a crew member would occupy, and for the first time somebody measured what a shielded human would actually absorb on that journey. The answer was 1.75 to 3.0 millisieverts a day in transit, about a third of that on the surface, and something close to a career limit for the round trip. Everything else in tonight's video is context for that one number. On April 1st of 2026, the gap ended. 4 people launched from Kennedy Space Center on a rocket built to leave Earth orbit, went around the moon, and came home 10 days later. It was the first time any human being had done that since December of 1972. And if you are old enough to have been alive for both, you waited 53 years and 4 months. This is the 8th section, and it is about what actually exists right now rather than what is proposed. If you watched it happen, you saw something no living person had seen since 1972. And if you did not, it is worth knowing that it was not a large public event in the way Apollo was. There was coverage, and there was interest, and there was nothing resembling the audience that watched the first landing. That is not a failure of the mission. It is what happens when something that used to be unprecedented becomes a repeat of something your grandparents watched. The engineering was harder than Apollo in several respects, and the attention was a fraction of it. Start with the vehicle, because it took a very long time to build, and the reasons are not flattering. The Space Launch System is the rocket. It is the most powerful launch vehicle NASA has operated since the Saturn V, and a good deal of it is descended from shuttle hardware, including engines that had previously flown to orbit and back on shuttle missions and were refurbished for a single expendable use. Orion is the crew capsule. It carries 4 people. It is designed for missions of weeks rather than the days Apollo managed, and its heat shield has to survive re-entry at lunar return speed, which is around 25,000 miles per hour, considerably faster than returning from low Earth orbit. Development ran long and over budget by margins that have been the subject of multiple critical audits. That is a matter of public record, and it is part of the honest picture. Artemis I flew in November of 2022, uncrewed, with an instrumented mannequin in the commander's seat carrying radiation sensors. It went around the moon and came back, and the heat shield came home with more erosion than predicted, which took most of a year to investigate and was one of the reasons the crewed flight slipped. The heat shield problem is worth understanding because it is a good example of why these programs move slowly, and it is not incompetence. Returning from the moon is a fundamentally harder re-entry than returning from low Earth orbit. A capsule coming back from the station enters at around 17,000 miles per hour. A capsule coming back from the moon enters at around 25,000. That difference sounds moderate, and it is not, because the energy that has to be dissipated goes as the square of the speed. Lunar return means roughly twice the energy to get rid of, converted almost entirely into heat. Orion handles it with an ablative shield, meaning the material is designed to char and erode away, carrying heat with it as it goes. It also uses a skip entry, dipping into the atmosphere, rising slightly, and entering again, which spreads the heating over a longer period and allows a more precise landing point. On Artemis I, the shield came home with more material lost than the models predicted, and in a pattern that had not been anticipated. Pieces had cracked and separated rather than eroding evenly. The investigation took most of a year. The conclusion involved gases building up inside the material during the skip entry and not escaping fast enough. The response was to change the entry profile rather than rebuild the shield, and Artemis II flew with that change. That is what a genuinely careful program looks like from the outside. A component performed adequately, in that the uncrewed capsule came home intact, and it was still enough of an anomaly to stop the next flight for a year, while people worked out why. Artemis II flew in April of 2026 with Wiseman, Glover, Koch and Hansen. There is a criticism of the Space Launch System that you will encounter if you read anything about it, and it deserves a fair hearing rather than being skipped. Each launch is expendable. The rocket is destroyed in use, including engines that in some cases had previously flown to orbit and back multiple times on the shuttle. Estimates for the cost per launch, including the capsule and ground systems, run into the billions of dollars, and government audits have said so in strong language. The counter-argument is that it exists, it works, and it is the only vehicle that has actually carried a crew beyond Earth orbit in the last half-century. You can hold both of those at once. It is expensive and it is real, and the alternatives that would be cheaper are not yet certified to carry people anywhere. I mention it because when you see coverage of Artemis, you will see both framings, often stated as though the other side is not arguing in good faith, and both are describing true things. Now the mission profile, because the shape of it matters. Artemis II flew what is called a free return trajectory. That means the path was chosen so that the moon's own gravity would swing the spacecraft around and send it back toward Earth without needing to fire an engine. If everything had failed after the outbound burn, the crew would still have come home. The path was designed to be self-correcting. That is the same principle that saved Apollo 13. When the oxygen tank ruptured, the crew got onto a free return path and let orbital mechanics do the rest. It is worth understanding that this is available at the Moon and is not available anywhere else, which is Section 9. The distance record from Section 1 comes from this trajectory. The spacecraft passed behind the far side and continued outward before turning back, which is why the peak distance of 252,756 miles is greater than the Moon's own average distance of about 238,900. You may be wondering why a free return matters if everything works, and the answer is that it is not about what happens when everything works. It is a property of the path itself. Choosing it costs a little efficiency and buys a guarantee that does not depend on any hardware continuing to function. Very few things in spaceflight offer that. Almost every other safety measure is a system that has to work in order to save you. A free return is a shape, and shapes do not fail. Now what is next? With the caveat that schedules in this field move, and these are the current published dates rather than promises. Artemis III is currently planned for 2027, and it is not a landing. It is a crewed test flight in Earth orbit to check rendezvous and docking with the landing vehicles. The crew was named in June of 2026. Randy Bresnik, Luca Parmitano, Frank Rubio, and Andre Douglas. Two of those names are worth a moment. Parmitano is a European Space Agency astronaut and is the one who nearly drowned during a spacewalk in 2013 when water filled his helmet. Rubio is the one from Section 2 who spent 371 days on the station because his ride home developed a leak. Artemis IV is the landing, currently targeted for 2028, aiming for the lunar South Pole. You should know why that target is different from anything Apollo attempted, because it is not a repeat with better equipment. Apollo landed near the lunar equator, on relatively flat ground, in daylight, with short surface stays measured in hours or a few days. The South Pole is rough terrain, in permanent low-angle light, with deep shadows that instruments struggle with, and the intention is to stay for far longer. The South Pole rather than the equatorial regions Apollo visited, and the reason is water. There are permanently shadowed craters near both poles where sunlight has not reached the floor for billions of years, and there is strong evidence of water ice in them. Water is the single most useful thing to find. It is drinking water, it is breathable oxygen, and split into hydrogen and oxygen it is rocket propellant. A destination that already has propellant is a fundamentally different proposition from one that does not. The water at the South Pole deserves more than a sentence because the evidence for it is a good story and because it is the reason the whole program points where it does. The Moon has essentially no atmosphere and no axial tilt to speak of, about 1.5 degrees. That second number is the important one. With almost no tilt, the sun never rises far above the horizon at the poles, and the floors of deep craters there never see it at all. Those are called permanently shadowed regions, and some of them have not received direct sunlight for billions of years. Temperatures in them have been measured at around -400 degrees Fahrenheit, which is among the coldest surfaces measured anywhere in the solar system, colder than the surface of Pluto. Anything volatile that arrives there, delivered by comets or produced by chemical reactions in the soil, has nowhere to go. It freezes and stays. The evidence came in stages. India's Chandrayaan-1 mission, carrying a NASA instrument, found signatures of water across the lunar surface in 2009. Later that same year, NASA deliberately crashed the upper stage of a rocket into a permanently shadowed crater called Cabeus and flew a second spacecraft through the resulting plume to see what came up. The mission was called LC-CROSS. It found water. More recently, an airborne observatory detected water on sunlit parts of the surface as well, in smaller quantities. So the South Pole is not a guess. It is the place where the coldest surfaces in the solar system have been holding onto material for longer than complex life has existed on Earth, and it is the closest thing to a resource depot anywhere off this planet. Now the honest assessment of where this leaves the question in tonight's title. Artemis is real. It has flown a crew, it has funding and named astronauts and a landing on the calendar, and the destination is the Moon. There is no crewed mission to any other body on any agency's schedule with a date and a vehicle attached. Not to Mars, not to an asteroid, not anywhere. Mars appears in long-term planning documents as an objective for the 2030s or 40s, expressed as an aspiration rather than a program. Private efforts have stated more aggressive timelines. Those timelines have historically slipped substantially, and I would not build a picture of the next decade on them, but the hardware being developed for them is real and is part of the Artemis architecture. So the 53-year gap has closed, and the itinerary has not changed. There is one further piece of the architecture worth knowing, because it is the part that would be genuinely new rather than a repeat. Gateway is a small space station intended for lunar orbit, not on the surface, not around Earth, but in a particular orbit around the Moon, called a near-rectilinear halo orbit, which is an elongated path that stays in continuous communication with Earth and requires very little fuel to maintain. If it is built and occupied, it becomes the first permanent human presence outside Earth orbit, and that would be the first genuinely useful test of everything sections 5 to 7 described, because it would put crews beyond the magnetic field for months rather than days, with modern instrumentation, close enough to come home if something went wrong. That is the missing rung on the ladder. Between 12-day lunar trips and 3-year Mars missions there is currently nothing, and Gateway would be the first thing in between. Its schedule and configuration have been revised repeatedly, and I would not put a firm date on it. One more thing about Artemis II, and it is the reason it matters more than a repeat of Apollo would suggest. It carried instruments to measure the radiation environment on a crewed vehicle. Continuing work, Artemis I began with the instrumented mannequin. Every flight beyond Earth orbit now is also a data-gathering exercise on the exact problem sections 5 to 7 described. We have measurements from Apollo, taken with 1960s dosimetry over 12-day missions. We have the Curiosity cruise measurement, taken inside an uncrewed capsule. What has been missing is modern instrumentation on a crewed vehicle beyond the belts. Artemis is filling that in, slowly, one short mission at a time, which is the honest version of progress here. Not a breakthrough, a program that flies rarely, gathers data each time, and builds a picture over decades. One thing about the timing of all this that you may find useful when reading future announcements. Every date in this section will move. That is not a criticism of anybody. It is the observed behavior of every crewed spaceflight program in history, including Apollo, which slipped repeatedly before it worked. Artemis I was announced for 2017 and flew in 2022. Artemis II was announced for 2024 and flew in 2026. So when you hear 2027 and 2028, the useful mental adjustment is not to disbelieve them but to expect them to arrive later than stated, by something in the range of 1 to 3 years, and to be pleasantly surprised if they do not. The thing to watch is not the dates, it is whether hardware is being built and tested, because that is the signal that survives schedule slips. That is the 8th section. Artemis II flew 4 people around the moon in April of 2026 on a free return trajectory, ending a 53-year gap and setting the distance record. Artemis III is an Earth orbit test in 2027 with a named crew. Artemis IV aims at the lunar South Pole in 2028, chosen because there is water ice in the permanently shadowed craters, and nothing on any schedule anywhere goes further than that. If something goes wrong on the way to Mars, you cannot. That is the 9th section, and it is the difference that makes Mars a different category of problem, rather than a longer version of the same one. It has nothing to do with radiation, and on its own it might be the harder obstacle. You already know the lunar half of this, even if you have never thought about it in these terms, because it is the plot of a film most people have seen. Start with the free return, because Section 8 introduced it, and this is where it pays off. A lunar trajectory can be shaped so that the moon's gravity turns the spacecraft around and sends it back. No engine burn required. If every system on the vehicle failed the moment after the outbound burn, the spacecraft would still arrive back at Earth. Apollo 13 is the proof. The oxygen tank ruptured about 200,000 miles out, the service module was crippled, and the crew came home by getting onto a free return path and using the lunar module as a lifeboat. They were back on Earth about 4 days after the accident. 4 days. That is the maximum a lunar crew is ever far from home in the sense that matters. Now Mars. There is no equivalent. Mars trajectories can include a free return in some launch windows, but the return time is measured in years rather than days, because you are not swinging around a nearby object, you are on an orbit around the Sun that has to come back around. The transit is 6 to 9 months each way, depending on the window. And once you arrive, you cannot simply turn around. Earth and Mars are both moving, and the alignment that made the outbound trip possible does not repeat immediately. A crew that arrives at Mars typically waits somewhere between 1 and 18 months for the return window, depending on the mission architecture chosen. Added up, and a realistic round trip is between about 2 and 3 years, of which the crew is genuinely unreachable for the whole duration. The reason the wait exists is orbital mechanics rather than caution, and it is worth understanding because it is the hard constraint that shapes every Mars plan ever drawn up. You do not travel to Mars by pointing at it. Mars is moving, and by the time you arrive, it has gone somewhere else. So you launch onto an orbit around the Sun that intersects Mars's orbit at the point Mars will be when you get there. The most efficient version of that is called a Hohmann transfer, worked out by Walter Hohmann in 1925, and it is essentially half an ellipse from Earth's orbit out to Mars's. That path takes about 8.5 months, and it only works when the two planets are correctly positioned relative to each other. The alignment that permits it comes around every 26 months, because that is how long it takes for Earth and Mars to return to the same relative geometry. Every uncrewed mission to Mars has launched inside one of those windows, which is why Mars launches cluster, and why they all leave within weeks of each other. Once you arrive, the same rule applies in reverse. You have to wait for the return alignment. That produces 2 families of mission plan. A conjunction class mission uses efficient transfers both ways and accepts a long stay at Mars, typically 500 days or more on the surface, for a total of around 2.5 to 3 years. An opposition class mission uses a less efficient trajectory to shorten the stay to a month or 2, but requires far more fuel, and often involves swinging past Venus on the way. The total is shorter, around a year and a half, but the crew spends more of it in transit, which is exactly the part that delivers the radiation dose. So the choice is between more time on a planet with an atmosphere and half the sky blocked, or less total time with more of it in the worst possible environment. Most serious planning has favoured the long stay for that reason, which means committing a crew for closer to 3 years. Now what unreachable actually means, in specifics, because it is easy to say and harder to absorb. No resupply. Everything the crew will consume for 3 years, every calorie, every filter, every spare part, has to be there at departure or manufactured on site. The station is resupplied every few weeks. A Mars crew is resupplied never. No rescue. There is no scenario in which a second vehicle reaches them faster than their own return window. If the return vehicle fails, that is the end of the mission and of the crew. No real-time communication. The signal delay between Earth and Mars runs from about 4 minutes each way at closest approach to about 24 minutes at furthest, so a question and its answer take between 8 and 48 minutes to complete. That last one changes the nature of the mission more than people expect. Mission control has been the defining feature of human spaceflight since the beginning, a room of specialists watching every parameter and talking the crew through problems in real time. Apollo 13 was saved by that room. At Mars, that room can offer advice that arrives half an hour late. Every immediate decision is made by the crew, alone. You can measure that isolation against the most isolated groups of people on this planet, and it does not come close. A crew at a research station in Antarctica through the winter cannot be reached for months, which is the standard comparison, and the source of a great deal of useful psychological data. But they are on Earth. They have breathable air outside the door. In a genuine emergency, aircraft have flown rescue missions in Antarctic winter at considerable risk and succeeded. A submarine crew is out of contact for months and is a few hundred feet from the surface. There is no group in history whose situation resembles a Mars crew's, and that is the difficulty with all the analog research. The analogues are all missing the feature that defines it, and there is a medical dimension that follows directly and is rarely discussed in the popular coverage. A crew member who develops appendicitis on the station is on the ground within hours. A crew member who develops appendicitis 8 months from Earth is treated by whoever is on board with whatever is on board. Over 3 years, for a crew of several people, the probability of at least one significant medical event is not small. Cancer, kidney stones, dental abscesses, fractures, psychiatric episodes, all of these occur in populations of healthy screened adults over 3-year periods at rates that are measurable. You can test how that delay feels against something you already know. A phone call has a delay of a few tenths of a second, and you notice it when it gets worse. A conversation with someone on the space station runs at close to normal speed, which is why you have seen live interviews with astronauts. At Mars, there is no conversation. There are messages, sent and answered, with up to 24 minutes each way. Nobody has ever operated a crewed spacecraft that way. Every crewed mission in history has had a voice on the other end in something close to real time, including Apollo at its furthest. That is a change in the nature of the job, rather than a communications inconvenience, and it has not been tested with people whose lives depend on it. Now the second half of this section, which is what the body does over that time, even if nothing goes wrong. Microgravity is not benign, and this is measured rather than theorized, because we have decades of station data. You have a reference point for most of this, which is what happens to somebody confined to a hospital bed for a long period. The bone loss, the muscle wasting, the cardiovascular deconditioning are recognizably the same family of effects, and some of the countermeasures came out of that literature. The difference is that a patient in a bed still has gravity acting on their skeleton. An astronaut has none, anywhere, for the whole duration, and the loss rates are correspondingly worse, Bone density falls. Astronauts lose in the region of 1% of bone mass per month in weight-bearing bones, and exercise regimes reduce that without eliminating it. Over 8 months of transit, that is a substantial loss, arriving at a planet where they then have to work. Muscle atrophies, particularly the postural muscles that no longer have anything to do. The cardiovascular system adapts to not having to pump against gravity and then has to readapt. Fluid shifts toward the head, and this produces the effect that concerns flight surgeons most. It is called spaceflight-associated neuroocular syndrome, and it involves flattening of the back of the eyeball and swelling of the optic nerve, with measurable changes in vision. It has been documented in a majority of long-duration crew members. Some recover fully, and some do not. That last one is a genuine unsolved problem. It was not anticipated. It was discovered by flying people for long durations and looking at their eyes afterward, and the mechanism is still being worked out. The immune system also behaves oddly in spaceflight, with dormant viruses reactivating in a meaningful fraction of crew members. The ones that show up most often are the herpes family, including the virus that causes chickenpox and then sits quietly in nerve tissue for the rest of your life. In spaceflight, it reactivates and is shed detectably in a substantial proportion of crew, usually without symptoms. That is worth knowing because it is not an injury caused by radiation or by weightlessness directly. It appears to be a stress response, and it indicates that the immune system is not operating normally, which matters a great deal more on a 3-year mission than on a 6-month one. There is a psychological dimension that has actually been studied, and the studies are more interesting than you might expect because of how they were run. A program called Mars 500, conducted in Moscow between 2007 and 2011, sealed volunteers in a mock spacecraft for durations up to 520 days, which is the length of a realistic Mars mission. The final crew of 6 men entered in June of 2010 and came out in November of 2011. They had no windows, an imposed communication delay, limited resources, and no way to leave without ending the experiment. The headline result was that they completed it. Nobody quit. The detailed results were less comfortable. Several crew members showed significant changes in sleep patterns, with one shifting toward a longer than 24-hour cycle and progressively falling out of sync with the rest of the crew. Activity levels declined over the mission. There was a general withdrawal, with crew members spending more time alone as the months went on. Similar work has been done in Hawaii at a habitat on the slopes of a volcano, with crews isolated for up to a year. The obvious limitation of all of it is that everybody involved knew they were on Earth and could be released. That is not a small difference from actually being 8 months away with no possibility of rescue. And the researchers say so. So the honest position is that we have studied the confinement and the boredom and the interpersonal strain, and we have not studied and cannot study the part where leaving is genuinely impossible. Now the honest counterweight, because everything above sounds like a wall, and it is not quite one. We know these effects because we have studied them on the station for 25 years, and the countermeasures have improved enormously. Crews now come back in dramatically better condition than they did in the 1990s because of exercise protocols, nutrition, and pharmaceuticals developed specifically for this. Valery Polyakov spent 437 consecutive days in orbit and walked from the capsule. So duration in microgravity is a problem that has been substantially managed, and there is an obvious engineering answer available for transit, which is to spin the spacecraft and generate artificial gravity. That is well understood physics, and it has never been flown because it adds mass and complexity, and nobody has built a vehicle that needs it yet. Which gives you the honest shape of this section. The microgravity problems are serious and partly solved and further solvable. The isolation problems are not solvable by engineering at all. The signal delay is a fact about the speed of light. The absence of rescue is a fact about orbital mechanics. No amount of money changes either. There is one more asymmetry worth stating. and it is the one that makes the moon genuinely different rather than just closer. If a lunar crew has a problem, the options are fix it or come home in about 4 days. If a Mars crew has a problem, the options are fix it. That is the entire list. There is no second item. Every system on that vehicle has to be repairable by the people using it, with the parts and tools they brought, at a distance where advice takes half an hour to arrive. No spacecraft has ever been operated under that constraint with people aboard. The station gets resupplied. Apollo could abort. Mars can do neither, and no amount of engineering changes that, because it is a consequence of where the planets are. That is the 9th section. A lunar crew is 4 days from home in the worst case, which is exactly what Apollo 13 demonstrated. A Mars crew is 2 to 3 years from home, with no resupply, no rescue, and a conversation delay of up to 48 minutes. The body's response to long-duration flight is measured and increasingly managed. The isolation is not an engineering problem, and there is no version of it that gets easier. So what would actually have to change? This is the 10th section, and it is the list of things that would move the itinerary past one entry. Some of them are engineering, some are research, and one of them is not a technical problem at all. Before the list, it is worth being clear about what is not on it, because you will see these offered as answers and they are not. More money is not on the list. Money would rebuild what Section 3 describes and would fund everything below. And it does not by itself change the transit time or the dose rate. A bigger rocket is not on it either. Launch capacity gets mass off this planet. It does not shorten the journey once you are on the way, because a chemical stage burns for minutes and then you coast, and a better spacesuit is not on it. Suits matter enormously for surface work and for solar events, and they do nothing against the particles in Section 5. Those 3 are the answers people reach for, and none of them touches the actual constraint. The first thing that does is speed, and it is the one that solves the most problems at once. Almost everything in this video traces back to duration. The radiation dose in Section 7 accumulates per day. The isolation in Section 9 scales with transit time. The consumables, the medical risk, the psychological load, all of it is a function of how long the crew is out there. Cut the transit time and you cut all of them together. Chemical rockets, which is everything currently flying, cannot do this. A chemical engine burns for a few minutes and then the spacecraft coasts for the rest of the journey on the velocity it already has. There is no throttle for the 8 months in between. The alternative that has been closest to real for the longest is nuclear thermal propulsion. A reactor heats hydrogen and expels it, producing roughly twice the efficiency of the best chemical engines. Ground testing was carried out in the United States during the 1960s and 70s under a program called NERVA. Engines were built and fired, and the program was cancelled along with everything else when Apollo ended. Development has restarted. A joint effort between NASA and the Defense Advanced Research Projects Agency has been working toward an in-space demonstration, and the target has been a flight in the late 2020s. Schedules in this area have slipped before. Roughly twice the efficiency does not halve the trip because the relationship is not linear, but published estimates suggest it could reduce a Mars transit meaningfully, perhaps from around 8 months to around 4 or 5. That is a real improvement, and it is not a transformation. It changes the dose from a career limit to a large fraction of one. Nuclear electric propulsion, which uses a reactor to power ion engines, offers far higher efficiency but very low thrust, meaning long spiral trajectories that can take longer overall despite the efficiency. It is better suited to cargo than crew. The NERVA program is worth a little more, because it got further than most people realize, and its ending fits the pattern from Section 3 exactly. It ran from 1955 to 1973 under various names, and it was not a paper study. Reactors were built and fired at a test site in Nevada. The most capable engine tested, called NRX-A6, ran at full power for 60 minutes continuously in 1967. Another, the XE Prime, was tested in a configuration resembling flight use and accumulated dozens of starts. By the early 1970s, the technology was assessed as ready for a flight demonstration. The intended use was a crewed Mars mission in the 1980s. It was cancelled in 1973, in the same wave of decisions that ended Apollo, for the same reason. There was no longer a mission for it to fly. So the propulsion technology that would most improve a Mars mission was tested to the point of flight readiness more than 50 years ago and then shelved, and the current program is in large part relearning it. That is the second time in this video that a capability was built, demonstrated and then discarded, and it is the clearest available illustration that the 53-year gap cost more than 53 years. You may be wondering why nuclear propulsion is not simply built, given that it was demonstrated 50 years ago and the physics has not changed. The answer is partly that flying a reactor requires an approval process that spans several agencies and takes years, partly that a reactor which has never operated in space introduces failure modes nobody has data on, and partly that until there is a mission requiring it, there is no forcing function to finish it. That last one is the same problem as Section 3 in a different costume. The technology waits for the mission, and the mission waits for the technology, and neither moves without a decision from outside. The second thing is shielding, and Section 5 explained why this is hard. The realistic approaches are not exotic. Use the mass you are already carrying. Put water tanks, food and waste in the walls. Design a storm shelter for solar events. Use hydrogen-rich materials rather than metal. Active shielding, generating a magnetic field around the spacecraft to deflect particles the way the Earth does, has been studied repeatedly. The problem is scale. The Earth's field works because it is planet-sized. Producing an equivalent deflection around a vehicle requires field strengths and power levels that no current technology approaches, and the field itself creates problems for the crew inside it. It is not ruled out. It is not close. The third thing is knowing what the radiation actually does, which is research rather than engineering. Section 5 said the biology is poorly characterized. That is a solvable problem in principle, and there is a facility for it. A particle accelerator at Brookhaven National Laboratory that can produce beams resembling galactic cosmic rays for biological experiments. What that cannot do is deliver a realistic exposure, because a realistic exposure is a low dose rate over months and an accelerator delivers a high dose rate over minutes. Whether those are biologically equivalent is precisely the open question. So the research is genuinely limited by the fact that the only place to run the experiment properly is the environment we are trying to certify. There is one variant of the shielding idea that deserves a mention because it comes up often and sounds like cheating. Use the fuel. A spacecraft departing for Mars carries a large mass of propellant for the return burn, and that propellant is sitting there for the whole outbound journey doing nothing. If it is hydrogen-rich, and if the tanks are arranged around the crew compartment rather than behind it, you get shielding at no additional launch cost. The problem is that the mass decreases as you use it, so the protection is best at the start and worst later, and the geometry of putting tanks around people creates its own difficulties. It is a real idea, it appears in serious design work, and it is a mitigation rather than a solution. The fourth is the medical and life support side. Closed-loop systems that recycle water and air with far higher efficiency than the station manages. Food production. Surgical capability. Pharmaceutical stability over 3 years, which is not a given because many drugs degrade. Those are engineering problems with no fundamental barriers, and progress on them is steady and unglamorous. There is a version of the life support problem that is easy to underrate, and it is food. A crew of 4 for 3 years needs somewhere in the region of 8 to 10,000 meals. All of it has to remain edible, nutritious and safe for the whole duration, and vitamin content in stored food degrades measurably over that timescale. The station manages by being resupplied. A Mars crew cannot be, which means either food that stays good for 3 years or growing some of it, and growing food reliably in that environment has been demonstrated only at the scale of a few plants. That is not a glamorous obstacle, and it is a real one. People have died on long expeditions from nutritional deficiency far more often than from anything dramatic. And the fifth is the one that is not technical. Somebody has to decide what level of risk is acceptable, and then be willing to defend that decision publicly if it goes wrong. Every number in sections 5 to 7 is a risk, not a certainty. A crew flying to Mars would not be certain to develop cancer. They would be accepting an elevated lifetime probability on top of the far more immediate risks of launch, landing, and 3 years of everything working. Somebody has to sign that, and the institution that signs it has to survive the outcome. That is not a physics problem, and it is not a funding problem. It is a question about how much risk a society is prepared to accept on behalf of volunteers who are willing to accept more. Apollo operated with risk tolerances that would not be approved today. Apollo 8 sent 3 men around the moon on the 3rd flight of the Saturn V, and the first with a crew, at a time when the previous uncrewed test had suffered significant engine problems. That decision was made in a matter of months. Nothing like it would happen now, and reasonable people disagree about whether that is progress or paralysis. There is a 6th item that belongs on this list, and it is the one that would change the arithmetic most, which is not going at all. Almost everything humans have learnt about the solar system was learned by machines. Voyager, Cassini, Curiosity, New Horizons, the Mars orbiters, the landers on Titan and on comets. Not one of them carried a person, and between them they have visited every planet. A robotic mission has no radiation limit that matters, no consumables problem, no return requirement, and no rescue scenario. Curiosity has been operating on Mars since 2012. Voyager has been flying since 1977. So there is a serious argument, made by serious people, that crewed deep space missions are the wrong tool, that the science return per dollar is far higher without a crew, and that the desire to send people is about something other than knowledge. I think that argument is largely correct on the science and largely beside the point on the motivation, and I want to be clear that this is my view rather than a finding. Nobody built Apollo to gather rocks. The rocks were real and valuable, and they are still being studied, but the program existed because a government wanted to demonstrate something, and the public interest in it was never primarily scientific. The same is true now. If the goal were maximum knowledge per dollar, the answer would be more robots and no crew, and everybody involved knows that. The reason to send people is that sending people means something different, and whether that meaning is worth the cost and the risk is a judgment rather than a calculation, which loops back to the 5th item. Somebody has to decide, and the decision is not technical. There is one more thing on the list, and it is the least discussed, which is practice. Nobody has ever operated a crewed vehicle beyond Earth orbit for longer than 12.5 days, not once in 65 years. Everything we know about long-duration spaceflight comes from low Earth orbit, inside the shelter, with resupply and rescue available. Everything we know about deep space comes from missions lasting under 2 weeks. There is no data at all on the combination that a Mars mission requires. Months outside the field with no way back. Gateway from Section 8 would begin to fill that in. So would longer lunar surface stays. So would a mission to a near-Earth asteroid, which has been proposed several times and cancelled each time, and which would have provided exactly this experience at a fraction of the risk. That gap is not a technology problem. It is an experience problem, and the only way to close it is to fly missions that are harder than the ones before them, in order, for years, which is what a program is, and it is what has been missing. Now let me pull every thread we followed tonight together. The furthest any human has ever been from Earth is 252,756 miles, set in April of this year by 4 people on Artemis II, breaking a record set by accident during the failure of Apollo 13 in 1970. 28 people have left Earth orbit. 12 have walked on another world. Every one of them went to the moon, and nowhere else. And no crew has spent more than about 12 days beyond this planet's protection. We stopped because Apollo was a Cold War program that ended when it was won. 4.4% of the federal budget became 0.4%. 3 completed rockets became museum exhibits, and 40 years of restart attempts died in the gap between engineering timescales and political ones. The Earth is wrapped in belts of trapped radiation, discovered because the first American satellite reported 0 when its instrument was overwhelmed. Apollo crossed them fast and at an angle, and the measured doses came out comparable to a medical scan. But the belts are not the hazard. They are the evidence of a shield, and the shield is what the space station sits underneath. Beyond it, galactic cosmic rays arrive constantly from outside the solar system. Every Apollo crew watched them pass through their own eyes as flashes of light in a dark cabin. Thin shielding makes them worse. Adequate shielding cannot be launched. The sun adds events on top of that background, arriving with minutes of warning. And in August of 1972, one of the largest on record fell in the 4-month gap between 2 crewed lunar missions. And in 2011, somebody put a detector in the seat a crew member would occupy and flew it to Mars. The answer was 1.75 to 3.0 millisieverts per day in transit. A round trip is close to an entire career limit. Apollo survived all of this because Apollo was 12 days. Meanwhile, a lunar crew is 4 days from home in the worst case, and a Mars crew is 3 years from home with no resupply, no rescue, and conversations that take up to 48 minutes to complete. Before the bottom line, there is one thing worth handing you to carry, because it is the part that changes how you read every space story you see from now on. When somebody tells you a mission to Mars is planned, the question that separates a program from an announcement is not the date, and it is not the rocket. It is what they say about the transit. If the answer involves reducing the journey time, or shielding the crew module with something specific, or a shelter design, then somebody is engaged with sections 5 to 7, and the plan is at least addressing the real problem. If the answer is about how many people will go and what they will build when they arrive, with nothing about the 8 months in between, then the hard part has not been addressed. That is a filter you can apply in about 10 seconds, and it works on almost every claim in this area. So here is the honest bottom line. The reason the moon is still the only place we have been is not one reason, it is 2, stacked, and they operate in different eras. For 53 years, the answer was that we chose not to. That is the deflating one, and it is the true one for that period. For right now, with a funded program and a crew that has already flown, the answer is different. The moon is the only destination reachable inside the time a human body tolerates being outside this planet's protection. 12 days is survivable, 3 years is not certified, and nobody can currently tell you how far from survivable it is, because the biology has never been measured at the dose rate and duration that matter. That is the terrifying part, and it is quieter than it sounds. There is no wall out there. There is no line that kills you. There is a clock, running the whole time you're outside, and the only destination close enough to get to before it matters is the one we have already been to. There is a way of putting the whole thing that I keep coming back to. For most of the last century, the assumption underneath every projection about spaceflight was that the difficulty scaled with distance. Further meant harder, and the history of exploration on Earth suggested that further would keep yielding to effort. That assumption turned out to be wrong in a specific way. The difficulty scales with time outside, and time outside is only loosely related to distance. A destination twice as far away is not twice as hard. It is exponentially harder, because the dose accumulates and the rescue options vanish and the failure modes compound, all as a function of duration. By that measure, the moon is not merely the closest destination. It is the only one on the near side of a threshold. And the threshold is not a distance. It is somewhere between a fortnight and a year of being outside the only shelter this species has. Nobody has ever crossed it. That is the actual frontier. And it is not where anybody thought it was. What is worth holding is the shape of the number. 253,000 miles. 65 years of human spaceflight, 28 people, one destination, and that is the furthest edge of it. Voyager 1 is 15 billion miles out. Our machines have gone 60,000 times further than our bodies, and the gap is not closing. If you remember one number from tonight, make it 252,756 miles, and remember that it is 4 months old and that it beat a 56-year-old record by 1.5%. That is the whole of it. Every human being who has ever lived has stayed inside that radius, and the only reason anybody ever reached the edge of it was a competition between two governments that ended before most people watching this were born. Thank you for joining me tonight on this trip out to the edge of where we have been. If you found this as fascinating as I did, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making these deep dives into the cosmos. Gene Cernan climbed the ladder in December of 1972, and nobody stood on another world for 53 years. 4 people went back in April, and they did not land. Good night.